One of the things the models can do is capture the they don't tend to have so reality
There will be more. It's here. In the US, it's really. Yeah, that's right.
Set to begin. We're going to introduce our speaker. So first of all, I will introduce
yes.
Julian.
People are probably wondering what I'm doing
Yeah,
here.
who is a colleague from, is it now the Department of Earth Sciences or Geophysical, something or
It's
other?
been
What's
Earth
his name?
Sciences for at least 20 years.
Earth Sciences, okay. Who will introduce our speaker?
Yes. So, like Frederi, I did my undergraduate education in France, where in mathematics circles, a joke went as follows. Without discussing mathematics, how can you tell that someone is an applied or a pure mathematician? Any clue? Well, the pure mathematician speaks French, and the applied mathematician speaks English. I'm not sure where that leaves Frederi, who speaks both very well. But he has actually, over the course of his distinguished careers, kind of straddled the boundaries between different areas of mathematics. And so even though he's now technically in a statistics department, he's always really been focused on the fundamentals of probability theory or stochastic processes. And that has led him to apply his mathematical talents to all kinds of applied problems, including climate science, which is why I'm introducing him here, because we have collaboration, but he's also done a lot of work in nuclear physics and the biomedical sciences, to name a few. So today he'll be talking to us about actually a rather old problem in statistics. And you'll see that it has some all kinds of applications, including with climate. So without further ado, Julien.
Thank you very much. Merci, Julien. Yeah, so I guess this is a dare for me to give the talk in French. Is that? So thank you very, very much to Susan and to Julien for arranging this. I'm really very humbled to be here today. And I'm also challenged with these devices here. So we'll see. I might just stay closer to the podium. So this is the plan of the talk here. I'm going to talk a little bit about what Yule's quote unquote nonsense correlation is. And then since this is an applied mathematics colloquium, there'll be some mathematics. Most of the slides that I've prepared are for mathematics. And so we might go through some of those quickly just so that you can see that there's some math there and then without having to read any of it. Since, as I understand, there's a significant proportion of the folks in the room who don't necessarily call themselves probabilists, I'll need to try to maybe spend a little bit of time explaining what the underlying objects are that we're using. And there's something which is called the second Wiener chaos. I didn't put the word Wiener, but I probably should have put the word Wiener there in bullet point number 2. And so we'll try to understand what those things are. I presume, maybe incorrectly, but you can correct me, that folks know what a variance is. I mean, I've spoken to some scientists who have a very, very weird notion of what variances are, but for mathematicians, it should be okay. And then convergence speeds, I think everybody understands convergence speeds in an applied math context. And so in a stochastic analysis context, it's the same thing. But maybe there'll be some subtleties which come from the probability side because we have convergences in various different forms. And so there's some very exotic convergence happening here, and some of that is called convergence in law. And I'll talk about some conjectures. And these are the names of the main co-authors with whom this work was done. And mainly, let's see if I can figure out which one of these is the pointer there. See, I told you that my fingers are too fat. It's hard for me to use this thing. Yeah. So, all right. So yes, Philip Ernst is the main contributor to what I'm going to talk about today, and he used to be at Rice University where I work, but now he's at Imperial College. And Soukana Douissi is a assistant professor in Marrakesh, Morocco. And this was partially funded by NSF and the Fulbright Commission. So we've all heard about time series. You can observe things, and in particular in the environmental sciences, sometimes the only thing you have, because like I say, sometimes there's no planet B. We only have one planet. So when you observe something over time, there's only going to be one series of observations for whatever it is that you're observing. And so imagine that you have two unique series of observation, S and T, and you think there might be some relation between them. So for instance, you observe maybe greenhouse gas concentrations in the atmosphere over time, yearly averages, and we have good measurements of those thanks to people like Julien and his collaborators. We have excellent measurements for some of these things, even going back in time quite far. And then T might be the temperature, the global mean surface temperature of planet Earth. And so you'd like to know if there's a relation between them. Of course, there's some deterministic reasons for that for a relation to hold, but there's also stochastic effects, and we want to find out if there's some independence between those things or not. So these two unique time series here, we only have one time series for each one of these two things, environmental observations here. They may, in a theoretical world, they may or may not come from independent phenomena. And this is one of the questions we're trying to figure out. Can we attribute something that we see? Let's see. So maybe let's get a show of hands here for folks who know something about causal inference in statistics. And I should lower my hand. Yeah. It's not an uncommon thing. But it has different interpretations in different fields. And in climate science and other environmental sciences, we might talk more about attribution of one thing to something else. It doesn't have the same rigorous notion of causality as you might have in statistics for those who want to try to develop that. But that's really what we're talking about. Can we attribute? It's not really a cause necessarily. It's an attribution. But actually attribution of literally. Attribution of phenomena that we observed, today or the past 20 years or looking forward 20, 30, 50 years, those kinds of attributions of certain things that we observe to the warming of the planet, to greenhouse gas concentrations. This is actually what makes the world go around right now, because every government in the world is trying to get their minds around what to do in order to put the brakes on climate change. So attribution, we're not necessarily saying cause, but yeah, attribution. And so again, as I said, since there's some folks in the room who aren't too conversant in probability, there's this notion of independence. Two different random objects might come from two independent experiments. But even if you're talking about unique time series, you can still ask the same question. Imagine in your mind that you're trying to devise a model that explains what this time series came from and what that time series came from. Imagine that world where it makes sense for you in your mind that you can devise those models, even if you're only observing one time series at a time. And in that case, if those two time series come from two processes which don't really influence each other at all, except in deterministic ways, then that means that the underlying noises which are responsible for the variations there are independent. But if those two time series come from a common phenomenon, which is, and then it really depends on how you want to interpret things. But if the common phenomenon is the greenhouse gas concentrations that we observe today were caused over time by human activity, like the common factor will be human activity, and that would explain why there's these correlations between these time series that we observe today and maybe, the concentration of CO2 in the ocean and, and how much CO2 there's in the atmosphere and how high the temperatures are and how fast the glaciers are melting and all these things, put together. So does that make sense, folks? Might make sense. All right. Okay. So that's, independence is really important, and we have this probabilistic notion of it to understand whether we can attribute something to something else or not. That's why we study testing for independence of time series. Make sense? Yeah. So that's what this whole story is about. And Yule was a statistician. So I'm going to maybe spend a little more time here on this slide. And again, when we get to the math, maybe we'll go faster. Yule was a statistician who worked in the 1920s and later, British statistician. And he, in 1926, he published a paper where he literally flipped a coin by hand and counted. He literally, because 1926, folks, right? How many people here remember 1926? Not too many. Yeah, one person in front running. Okay. So he literally flipped a coin by hand and then counted over time how many heads he counted +1 for a head, -1 for a tail, and made recordings of this and did this a number of times, and then did this with one coin on one corner of his office or home, and then he did it with a different coin in a different corner of his office with the left hand And then so that those two sequences of coin flips would be, I don't know how he did, okay, right? But it's in the paper. And then those two sequences of coin flips would, would be independent of each other. And then what he did, this is what he did. Listen to this. So you'll recognize it. Okay, I'm gonna put this down because it's not working. So yeah, my fingers are too fat, and so we kind of missed the tea, but if maybe we can hang out afterwards. If you want to know why my fingers are a little too fat, you can ask me later. So you might recognize this thing. This is known as Pearson correlation coefficient, and folks in the applied sciences know about this. They use it all the time. When you have two sequences of independent data, if the data themselves are independent within each sequence, if like every time you pull a number from your sequence, it doesn't depend on what happened in the past, or if the dependence is very short in memory, it doesn't depend on the distant past, then when you compute this correlation statistic between the one sequence of numbers that you have for your one phenomenon and then the same one for the other phenomenon, if those two phenomena are independent of each other and you have enough observations, this correlation statistic will converge to zero. Not super fast, but fast enough that you can tell from looking at what rho n is actually equal to with your longer time series, whether there's a good argument to be made that we cannot, and as we say in frequent statistics, we cannot reject the notion that the two sequences come from independent processes. So you look at this number rho, if n is large enough, it'll be difficult for you. If n is large enough and rho n is close enough to zero, it will be difficult to reject the notion that these two time series come from independent processes, which means that you cannot do that attribution that you so badly want to do because of the IPCC. Anybody heard of the IPCC here? Yeah, one person. Oh, okay. All right. Okay. So I guess I won't go into the details there. All right. So, but yeah. So that's the story. And Yule discovered, let's see here. So what I was just explaining now is what's at the bottom of this slide. There's something known as a central limit theorem. Raise your hand if you heard of the central limit theorem. About a third of the hands go up. Okay, so we don't have to dwell on that. As I mentioned, the result that you will be able to detect impossibility of rejecting the notion that the two phenomena come from independent processes. That impossibility to reject that so-called null, if you've done any frequent statistics, you've heard of the notion of null hypothesis. That's what I'm talking about here. Cannot reject the null. It persists not just if you have i.i.d. data, independent and identically distributed data, but even for short memory stationary time series, which are things which occur frequently in natural phenomena, but not all time series which we observe and that we're interested in are stationary. And this is what I was talking about 5 minutes ago. Yule noted this. And so, and what he noted is that the rho n that I had at the bottom of the slide on the previous one is, even if n goes to infinity, that rho n will actually be diffuse. So Yule actually graphed in his paper the shape of the distribution of the values of rho n that he was getting when he repeated this experiment a number of times with two independent time series, when he was actually counting the number of, the total number of pluses and minuses that he was getting when he was doing these coin flips. And those numbers of pluses and minuses, these are known as random walks. Raise your hand here if you've heard about random walks. Yeah, a little bit more than half. Okay, good. So random walks are accumulations of things that happen over time. Very, very different behavior. If there's one thing that I'd like you to remember from my message today, my kind of bottom line up front is that random walks have a very, very different behavior than a stationary behavior. Random walks have a tendency to grow over time. In fact, we know how fast they grow. They grow like the square root of the number of data points. And stationary time series have a tendency to be stable and to come back to some mean level. So very, very different behavior. So you'll observe that rho n actually is diffuse over time, does not converge to anything near zero. But in fact, it was noticed a little bit later, like maybe 20 or 30, 35 years later, that you can set up a limiting problem and you can look at this expression here, and I'll explain this bottom line in a second here, which is where those y's are defined. It turns out that as n goes to infinity, the probability distribution of rho n that I had on the previous slide converges to the probability distribution of this so-called random variable. So let me explain what this object is, so you can get a sense of what the limiting object is that we're looking at. W1 and W, so you see how I and J, oh, I don't have it here, but I and J are equal to 1 or 2. And so you have a numerator where the IJs are mixed, and then you have I equals 1, 1, and here 2, 2. And these quantities here are defined using this expression. It's a little hard to tell because this is only a 1-hour talk with, and you may not have been trained with stochastic processes, but W is what we call a Wiener process. Both of these W's are Wiener processes here. Wiener processes, it turns out, Wiener processes are the continuous time analog of random walks. Discrete time, continuous time, we know what those things are. If you try to take your random walk and you try to force it into a box where you can count time continuously, the object that you get is the Wiener processes. Now raise your hand if you know who first described Wiener processes mathematically. And those of you who know the answer, it was, so there's this notion, this is just an interesting like historical thing. There's this notion that the Wiener process, which is known by a different name in different contexts, some people call it Brownian motion, mathematical Brownian motion. A lot of folks think that Albert Einstein is the one who discovered the mathematical version of this Brownian motion in a paper in 1905 or 1906, I forget. And so that's like the common knowledge that that he was such a genius. Not only did he the special and general theory of relativity, and I forget what the fourth paper was that he had in 1906.
Photoelectric effect.
There you go. But one of these papers was Brownian motion. It wasn't him though. No, it was Louis Bachelier, who was a PhD student of Henri Poincaré in 1900, published in his dissertation, The Mathematical Construction of Brownian Motion, for a purpose, by the way, not related to my talk, but just so you know, for the purpose of understanding financial markets at the time, which 73 years later, people by the names of 69 and 73 years later, Merton, Black, and Scholes used the same Brownian motion, which has by that point had been studied ad nauseum, to study the same question in mathematical finance, the same question about how to price options on a financial market, and they got a Nobel Prize in 1997 for the work that they'd done. And it was only, I'm not even sure when it was discovered that Bachelier had figured this out all by himself in his corner, while his PhD advisor was telling him that this was terrible work and it made no sense, because as I claim, Poincaré did not understand any probability, and that's why this guy was not recognized. In any case, these are the objects that we're dealing with. You can see we have here this quantity rho, which is the continuous version of this correlation that we had on the previous slide. And so it's good to know that the reason why rho n does not converge to 0, even if your two time series are independent, is because it converges to something completely different, to a random object, which is not at all 0. You can see that right there, that it's not 0, just because there's a formula for it, which is clearly not 0, it's random. Make sense, folks? Yeah. So that's why the word diffuse in there means that it's just random and it's not at all 0. Okay. Clearly rho is diffuse. And then real quick here, maybe we won't dwell on this too much, but Philip Ernst solved a mathematical question related to this thing, which had been open since Yule asked the question in 1926. Can we actually compute the variance of rho n or the variance of rho? Philip Ernst in 2017 solved that question. I mean, it was a 90-year-old problem because it was kind of asked by Yule originally, but Yule asked it in the discrete time setting, and he solved it in the continuous time setting. But he became very famous for this after he published his paper in 2017, because people literally thought that they would never be solved. So one of those types of problems. But he did the calculation using tools that nobody had ever seen before. And they're tools from, and here I'm just advertising for the genius of Philip Ernst, my friend, who lives in London now. Just tools from classical analysis. You got to have a lot of guts and grit in order to use tools from classical analysis when the best probabilists and stochasticians in the world had tried on this problem for 50 years and couldn't get anywhere with it. But he just used old school hard analysis tools with a bit of talent in computing determinants and just ordinary linear algebra. That's how he did it. And then we also looked at a related problem, which is what happens. This is with my colleagues from Morocco and Kuwait. Where we looked at this exact same object, but when the process W is not a Brownian motion, not the limit of a random walk, but what happens if you replace it by something which is a self-similar process? Well, we have a comment on that. And also in that same paper, we look at the case of stationary processes, which gives us a completely different answer. In that case, rho of t or rho of n does converge to 0. But let's skip that. All right, so you can ignore the first bullet point here. Why are these questions important in practice? But I explained that at the beginning of the presentation today, and this is recorded, right? Yeah, so we're good. Pardon me?
I believe it's being recorded, yes.
Should I check?
It does, it is, it says at the top.
Ah.
There's a little red dot saying recorded.
Oh, rec, yeah, okay.
But we won't know until we open the box and look inside, so.
Yeah. Yes, so this is what I explained at the beginning, actually. Oh, and then I just want to say a few words about the last line on this slide. This is something which I've been fascinated by since around 2010. Anybody here been to Africa? Any part of Africa, including North Africa? Yeah, cool. Well, there's a part of Central Africa. It's kind of on the north side of Central Africa, kind of on the it's Central Africa, which is called Lake Chad. Heard of Lake Chad? It's a pretty big lake. I like to call it Africa's Great Oasis. It's the flattest, it's the shallowest lake in the world because it's so shallow and because it's so hot. It's in the eastern Sahel. Because the temperature gets so hot in the summer that evaporation rates are extremely strong because this lake is so shallow. And so its volume, its area, and even its volume vary dramatically every single year. And so because of this, and it's an oasis, it's not like a desert oasis where there's always water. No, this one's so shallow and so big that the area just varies dramatically every single year from the dry season to the wet season. And there was a situation where some American scientists in the early 2000s had decided that because this Lake Chad region was coming out of two extremely severe droughts, those of us who are old enough to remember the famine in Ethiopia, around the same time there was also famines going on in the eastern Sahel, actually the whole entire Sahel, which is the part of Africa which is between the Sahara Desert and more tropical Africa. And so there's plenty of reasons why the amount of water that was falling from the sky during the 1970s and 1980s was much lower than what had been experienced in previous decades. Some of it might be due to climate change, maybe not. It's a little hard to tell. I guess the jury's still out. Nobody's really studying that question. But one thing that really bothered me is that I found out after discussing the issue with Lake Chad with a specialist, actually turns out a French hydrologist who grew up in Chad, one of the colonizers. He told me, yeah, you check out this paper. I talked to the authors, and this paper had gotten a lot of press, and he tells me that the authors had admitted to him that they weren't sure that the paper was all that good. And this paper claimed that one of the reasons why Lake Chad was missing a lot of water up to that point, since the drought started in the 1970s, was because the farmers in the northeastern side of Nigeria, of Lake Chad, which is in Nigeria, were just taking out too much water from the lake. That was there. I mean, we know that this sort of thing happens across the world when you try to implement, industrial methods. Like you've heard of the Aral Sea, which, I mean, it used to be a sea. It's there's nothing left of it now. The Soviet Union made sure of that when they started growing cotton in Uzbekistan. But this is not what was necessarily going on in the Lake Chad area. These are, very modest farmers, people who really don't use large-scale irrigation. And so they managed somehow to find a correlation between two time series, one which was the amount of water that they estimated was in the lake, or maybe the lake area, and the other was an estimate that they had of how much water was being used by farmers, or maybe it wasn't even the water, it was just how much activity was going on in farming, in animal farming or cropping in the area over like maybe a 20-year period. And so, number one, like you're going to find problems with the people who live in this part of the world. How about you blame somebody other than those who are actually suffering from it, number one. So that would be my first reaction. And then number two, what they did is they used a lake or a volume or area, and that's an accumulated level. It's like a random walk. And so right away, after I found out from Philip Ernst that this is a problem that a lot of scientists are guilty of using incorrect attribution because they're looking at time series and correlations of those instead of using it in the proper context, I thought, well, this is most likely this is why this paper is wrong. They're trying to use this nonsense correlation, which was first described by Udny Yule, and applying it in a case where they're actually picking on the weaker man. So this is driving me nuts. And so I'm telling you this story only because it is related, and this is part of our plan. We have a project now, which is funded by the British Academy, which is British Academy is the equivalent of the National Endowments for the Humanities in the US. And so the British Academy decided, we wrote a proposal with Philip where the angle was really on social science and economics and not on the math. And we told the story, and I guess they liked it because out of 150 applications that they received, only 7 got funded, including ours, and we're the first statisticians to be funded by this scheme. So I'm pretty happy. So we're studying this, and I'm going to make a connection. By the time we're done with this study with Lake Chad in a couple of years here, hopefully we're going to go to Chad. We're going to go to Northeast Nigeria, collect some data from what the farmers have to say, and maybe say a little bit more about why that original And there's a lot more to this story, so you can ask me later, but why there's a lot of nonsense in what people have said about what's going on there, based on incorrect attribution, based on the use of Yule's correlation statistic, which should not be used in that context. So here, for those who are who like math and don't necessarily understand these Gaussian objects, the tool that we use here is stochastic calculus, or on Wiener space, or Wiener chaos calculus. And the quantities that I had written previously, y1, 2, and y1 and y2, 2, can be re-expressed. This is just some simple, I guess, algebra that you would do in order to find. Check it out here. We have the W1 and the W2 that I was talking about before, and now they're in differential form because we're integrating against them. You may not have heard of stochastic integrals, or you may have. Well, stochastic integrals are a little bit tricky to find because these W's are not bounded variation processes. You all have heard that Brownian motion, the Wiener process, is not of bounded variation. So if you know a Stieltjes integral, you can know a Stieltjes integral when you see one, right? Mathematicians know this, right? This is not what these are, because these processes they don't even have a bounded they have a bounded quadratic variation, but not a bounded variation. So they're very far from being bounded variation processes. So it's a little tricky to define these objects, but we can do it. And these objects are all random. And this process y12, it just helps to write it this way. And lucky for us, in the case of the Brownian motions, we actually know exactly what that kernel is. It's here on the bottom. So this is helpful to us. When we have this all set up, these are objects which live in the so-called second Wiener chaos, because they involve double integrals with respect to one or two different Brownian motions. And so I don't know how much of this, because I do want to tell a few more stories here. And at the end, I think I was thinking of maybe writing on the board some stuff, that's related to the work that I'm doing with Julien that we're looking forward. But I think I might just talk instead of writing down. But I want to get to that point. So here, what you see on this slide is more comments on how these objects behave, which is so one of the things when we're talking about attribution, let me try to use this clicker here, then I don't have to walk back and forth. So my apologies, everybody. I really am old school. So remember, you had this W1 and W2. And so in order to tell whether the original processes or time series or random walks can be attributed to each other or not, you really are asking yourself, especially in this very linear type context or bilinear, are these two W's, correlated, or are they not correlated? And so here, this I think anybody can appreciate. Let's say that W1 and W2 are correlated, and they're so-called Gaussian objects, which is really one of the simpler objects that we can use that we can study in probability. They're Gaussian. You've heard of the Gaussian distribution, like at least a bell curve, right? Bell curve, anybody? Makes sense? Yeah, bell curve, we see those things in the New York Times all the time, right? Some of them look like bell curves, right? So bell curve, Gaussian, same thing. You have two different random walks or Brownian motions. They might be correlated with each other. When does that work? How do we model correlation? This is just simple, very simple mathematical modeling. We say that W1 and W2 are correlated if the value R in this formula is non-zero, which means what? W2 really depends on W1 because you need W1 in order to compute this first part. And then the other part is whatever else you need in order to make sure that your W2 is the type of object that you were claiming in the first place. So here's the formula. It turns out when you analyze what these objects look like, you have a very nice formula for how W1 and W2 could be correlated with each other. And here, how to get the formula to work, you say, well, W1 and W tilde are two different Brownian motions, and we use this orthogonality symbol here, probability, to denote independence. So you have two independent Brownian motions, use both of them to create a third one. That's when you get two correlated Brownian motions. Make sense, folks? This is like just an ordinary mathematical linear regression, very simple stuff. So you set it up this way, and then you look to see whether you can reject the idea that R is zero. Can you reject the idea that R is zero? That's our attribution question. And sometimes you can, sometimes you can't. And if you're using the wrong tool, you have to then go back to the drawing board and see what it might mean. Okay, so let's see. This is probably just all nonsense. Yeah. So you discretize things in time. The paper that I wrote with Philip Ernst and one of his students looks at the same question of computing the variance of this correlation rho, except we decided to actually bite the bullet and try to do it not for rho, which Philip Ernst did in 2017, but for the actual rho n, which is in fact exactly what Yule wanted to do. for n fixed, let's say n equals 500, like a random walk of that size. Can we do it? Can we compute? Mathematically, maybe it's an interesting question. We certainly thought it was. The paper is now published in Stochastic Processes and Applications. And then let me just zoom through these slides so I can show you some of the difficulties that we ran into in trying to do the math. So as I said, our mathematical interest, and there's some applied reasons why computing this variance should be important, and I'll say more about the applications of all this in a little bit. But here, as you can see here, there's a tool that we use. Well, we first define the so-called alternative characteristic polynomial of this matrix K, which is the discretized version of the other one that I had at the bottom of several slides ago. And then it turns out something that Philip discovered a few years ago is that you really want to concentrate on trying to compute this so-called trivariate moment generating function, which is kind of like a Laplace transform. Everybody knows Laplace, right? Yeah. So turns out that's the thing to do. So zooming through here, I think maybe I went too far. Let's see. So then there's a theorem that was not in the original paper in 2017, but Ernst and two other colleagues here figured out this general expression for the expectation of the nth moment of your random object of interest here. So the nth moment is the expectation of the nth power. Expectation just means mathematical average. And there's a formula to do that with some partial derivatives if you can get a handle on this function phi. And it's feasible. Maybe it is. Maybe you're lucky. Maybe it takes a ton of elbow grease. As I say here, we only need to find this function phi n and hope that the moment calculation afterwards is tractable because it just depends on the mixed partial derivative of phi, whatever. Turns out, yes, we can compute this characteristic polynomial. It's horrendous, but it can be done. And it takes a little bit there's a couple tricks involved. But at the end, you get a second order finite difference equation, which is stuff which I think they teach in undergraduate school, maybe even in high school. So like what I'm saying is the tools that we use are classical tools, but they're nothing that anybody who's in their sane mind would try to do because it's just very complicated, but it can be done. And even with this extraordinarily complicated determinant calculation out of the way, applying it to the moment formula takes also some elbow grease, which leads us to this expression. So I told you that I was going to flash these slides, right? So that's it. But then, so, this is nice, right? That we can do this now. We can flex our muscles and we can say, ask me to compute a determinant. Come on, ask me to compute it. So, and we did it, right? But that's maybe not as interesting as the question of the speed of convergence of rho n to rho, and I'll try to explain in the next 10 minutes or so why this is so critical in our mind. How fast does the discrete object converge to the continuous object? We have our Brownian motions over here. We have our random walks over here. These are those correlation coefficients. For Brownian motions and random walks, rho n does not converge to 0. It converges to rho. It converges to rho in law, and I'm not talking about my in-laws. It converges to rho in law, which means that the probability distribution of the object on the left, which depends on n, is a function, if you will, that converges in a certain functional sense to the probability distribution of the random variable on the right. Make sense, folks? Yeah. Okay. So it's a functional convergence, and there's several different types. There's a number of different modes of convergence, but the weakest one is well. Okay. So here's one mode of convergence. This is so-called the Wasserstein distance, which is defined this way, and it turns out this is a kind of a key. So this is for the probabilists in the room. I'm going to get just technical just for a second. It turns out that the Wasserstein distance is bounded above by the ordinary L1 distance if the sequence rho n and the limit rho can be defined on the same probability space. In other words, can you find a coupling where rho n converges to rho? And if they converge in L1, that's stronger than Wasserstein distance. Make sense? So that's really cool. Then it's just a matter of trying to find the right coupling. Again, this is a little technical. And then right, which is this expression. This is the thing that we're after, to find out how fast the convergence occurs. And maybe if we can find out how fast the convergence occurs, there's some actionable ideas that we end up with on the statistics side. There's some technical tricks that we use here, more elbow grease that you can see down here. And then so this is really unusual. we really didn't need to do this. This is a total overkill. We were able to compute the variances of the objects of interest. These are second chaos objects. People like just don't, they will shy away from this sort of calculation. But everything is so explicit in this particular case that we're working with these random walks that we can actually literally compute exactly what these variances are. Look at this. And you might have heard, y'all are applied mathematicians, you might have heard of Falaber's formula, which we use ad nauseum, and that's how we come up with these expressions. So this is, again, stuff that existed maybe 150 years ago. And it's just that people don't want to use these tools anymore, but we do. And so our final result is that the Wasserstein distance converges at this rate, which is fast, by the way. Again, raise your hand if you've heard of the central limit theorem. Anybody? Central limit theorem, yes? How fast? What's the speed of convergence, like the basic one in central limit theorem? 1 over square root of n, yes. Yeah, climate scientists know this. This is better, am I right? Yeah. And this gives us a clue that this is not a central limit type phenomenon because the speed is faster. So that's critical. Yeah. So, okay, so I guess I could just skip this, but in the end, we do get, what we want in the end. And then, so these objects, y11 converges to y11n converges to y11, same thing with y12, y12. And then you can, by polarization, all this is kind of trivial. You can ignore the top line there. It's just some technical thing that, in the interest of time, I'm not going to try to explain it. But what's down here, interestingly, again, these second chaos sequences in the second Wiener chaos, these second chaos objects have a very specific structure. They're infinitely more complex than Gaussian objects because they're products of Gaussians and they're sums of products of Gaussians. So whereas a Gaussian variable could be characterized by just a couple of parameters, let's say the mean and the variance, for a second chaos object, you need infinitely many parameters. That's how the world works in these probability models. But then you can ask yourself, so when you have convergence well, then you can ask yourself, what kinds of limits can I get, at least in law, for a sequence in the second chaos? What are the allowable limits that I can actually imagine? The answer, it turns out, there's really only one class of limits that you can get. For any second chaos sequence, the weakest form of convergence that you can think of is convergence in law. And the only real legitimate types of limits that you can get are Gaussian limits, second chaos limits, or convolutions of the two, which means that in law, your limit will be a sum of two independent terms. One is Gaussian and one is second chaos. And this is a theorem which was due to Nourdin and Pauly in 2012. Nourdin et Pauly, just so we're clear. And then in our case, we may need a trivariate version of that theorem, but it's okay. We think that the second chaos component, so as I said, the possible limits are, we need to figure out what these limits are because we need them to understand the dynamics of the large time dynamics. We think that, there's the sum, a Gaussian part, a second chaos part, you sum them together, they're independent. We think that the Gaussian part might be 0, but the second chaos part is not. And in our case, this is work in progress, all this, but we're pretty sure now because we did a lot of the calculations already. We think that a couple of things can happen. Well, we know that a couple of things can happen. One way that you can get a second chaos limit for a second chaos sequence is if the second chaos component in the Nourdin-Pauly theorem converges in the so-called L2 of omega space, which means that it's in physical space. You have convergence, you have an object which is in its own physical space, which lives on one single so-called probability space. This is getting technical for the probabilist here. And the limit is in the second chaos. And so one way to do that is, well, the limit is going to be in this space L2 omega. And that happens if and only if the so-called kernel in the kernel representation of your second chaos object converges in this underlying Hilbert space. Okay, great. But that is not what ends up being true here. Rather, we believe our second chaos component converges to a so-called product normal distribution, which is a very specific type of second chaos object. Product normal, it's funny how, no offense to all my colleagues, and they're all very learned. Product normal, do you teach that to your grad students? Do they know what that is? Product normal distribution? No? What do you think it is? The product normal distribution is the product of two normal distributions. You take their product and you look at what law you get. That's the product normal. It's the product of two normals and you look at the law. Like a log normal, if you take the log, it's normal, right? Yeah. So product normal. So that's what we're getting here. We get a product normal. It's even more interesting than this. And this is not predicted in the theorem of Norden-Pauli because it's a little subtler. One of the two normals in this product normal comes from an actual CLT. It's a normal. It might actually come from a CLT. We think that's true. And the other one is Gaussian because our underlying objects are Gaussian. Normal, Gaussian, those are two synonyms. It's Gaussian, but it's observable. It's observable. It's a linear functional of the data that we had to begin with. And the Gaussian distribution has this property that you start with a high-dimensional Gaussian object. You torture it any way you want, as long as what you do is linear. The object that you get in the end is still Gaussian. And so that's how these two parts of this product normal, one of them is a linear transformation of your original Gaussian data, and the other one comes from a CLT. And a CLT is something that comes from outer space. It comes from a different world. It's an effect that you get only in the distributional sense. It's not a real thing. Like, have you ever thought, I mean, this is how I see it now. The CLT gives us an object which is not for real, right? Whereas here we have two things. One that comes from the CLT, which is an imaginary thing, kind of like volatility. It's imagined, right? $4, those are imagined too. And then the other one comes from the actual data, and it's a linear transformation of the data. So if your data is Gaussian, then your object in the limit is also Gaussian. We think this is what's going on, and we also did the math, and we think we know exactly what it is. But proving it is, we need a little more time. So that's our conjecture. So since I'm running a little bit out of time, and I want to talk about the stuff that Julien and I are interested in as well, I may skip this, but here, so let me just try to explain the implications for testing. So if our conjecture that I just talked about with this product normal as a limit is true, there's something which is called the delta method. You can ignore it. Well, yeah, so there's a function here, and this function is a trivariate function. It's the function f of tuv is t over the square root of u times v. So it's the function that you need in order to create these rows and these row ends. It's that function. So it's a very clear function. You can take its gradient. This u here is the product normal limit in distribution. That's what that u is. I'm sorry, no. The u is the one part of the product normal that comes from the observable. And then the sigma is the so-called covariance matrix. It's the covariance matrix of the CLT side of things. You put all things together, you mix them up the right way using this so-called delta method, and you find that because we already noticed that n was the speed of convergence and not square root of n, you remember that, right? So rho n minus rho multiplied by n has a non-trivial limit. It's asymptotically normal with a mean of 0 and a variance which is equal to this object, and this object is random because the u depends on your original data. So it's this is a conditional CLT. It's so exotic that it's a conditional CLT where the speed of convergence is 1 over n. How's that? So this is fairly exotic. I've seen some conditional CLTs before, but they weren't CLTs in which the standard deviation is a normal object. They were CLTs where the standard deviation has to do with the so-called local time of some other crazy process. It was just a complete mess. It's not at all. Like, this is much simpler. So we have an example. This is the first example I've seen of a conditional CLT, which is this simple, because the underlying objects are simple. And therefore, we could reject the so-called null hypothesis that W1 and W2 are independent if this quantity, which is supposed to be distributed like this, deviates enough from 0, but based on a variance which you have to pick up from the original data. It's data dependent. So it's just an ordinary use of ordinary CLT, with a faster speed of convergence, which is great, which means we need less data. This is a faster speed of convergence. And you have to compute your asymptotic variance using the original data itself. It's kind of nuts, but this is our conjecture now. So that's where we are. And then, so that's it. So I guess, I don't know who's keeping an eye on the clock, maybe 10 more minutes?
10 minutes, yep.
All right, thank you. So I didn't actually prepare notes. I thought I had my laptop out here. So I'll tell you what, I'll just, Julien, if it's okay with you, I'm just gonna talk without writing things on the board for what we've been talking about. Okay. So one of the things, so as you can see, this is one method for doing attribution with climate time series, even if one or both of your series are structured like random walks rather than stationary phenomenon. And so another thing which is closely related to this, and we're still trying to work out some of the conceptual details, is, and here, Julien, if I misspeak, you're going to have to correct me here, because so this comes from paleoclimatology, and we're dealing with observational time series. We would like to try to reconstruct the temperature of planet Earth on a yearly basis on average, maybe for the northern hemisphere because there's more continents there, for instance, over the last, let's say, 2,000 years, which I think is the period of interest for these folks. And so that's a reconstruction of what might have happened based on a number of things. And then different research groups in climate science have different interpretations of how to take the data that's available and use it to create a new model, which gives us a reconstruction of those past temperatures. So we have disagreements, and some of this I'm still not totally clear. So if you think it's necessary, you should interrupt me. So some of these research groups publish what we like to call ensembles. So these are clouds of possible trajectories that the modelers say are representative of what happens with the randomness in their reconstruction. So there's some uncertainty on what these past temperatures were like. Just like there's uncertainty perhaps on some of the models that we're constructing here for where we actually just look at one observation of what happens over time in one specific variable. So this construction here, you have an ensemble, which is one way to represent uncertainty on the reconstruction. And you also have groups of researchers who publish a so-called trace. You might have a model where the researchers decide that they want to publish one possible past of planet Earth over the last 2,000 years in terms of the global average temperature, and they call those things a trace. And so then my understanding is that we would like to maybe take the trace that's coming from one group of researchers, look at two reconstructions with uncertainty which come from two other groups of researchers, and see which one of those two fits better to the trace. Is that kind of one way to say it? Yeah. And then so it turns out that this is what I've understood by working with Julien and his colleagues. When you pick out one trajectory from your ensemble, that could be representative of the temperature. Let's say that these ensembles are representing temperatures, and we've had a heck of a time trying to figure out a model in time series theory that actually fit these ensembles. And so what we've decided to do in this paper that was just released on Earth Archive, just a couple of months ago, is to treat things in a completely empirical way. But we would like to do things more mathematically. All right, so putting aside, I really encourage everybody to read the paper because it's really fascinating. And at the end of the paper, we have some discussion of what might actually happen as applications for other fields. And in the appendix of the paper, we explain some of the math behind some of the choices that we made. But we would like to do things a little differently. We'd like to be able to say, we're picking one trajectory out of this ensemble, and then we look at that one trace. And we're going to do this for the same group of researchers coming from this other ensemble. Well, how would we compare these two ensembles to this trace that we pick up? Well, one idea that we had was to create an epsilon ball. Maybe I should write it like this because time is in the horizontal axis. Time runs from 0 to minus 2,000 in the horizontal axis, and you have this trace that we decide to compare things to. Then we create a epsilon ball, if you will, with the radius epsilon and some metric like the sup norm, if you'd like, around this trace, and we'd like to be able to figure out, according to this model or according to that model, what might be the density of the probability model around this particular trace for this particular model and for that one. And so using ideas that come from statistics, whichever one of these two models has a density which is higher should be perhaps the one which fits the best. It's kind of like the idea of maximum likelihood, if you will. You might have heard of maximum likelihood. That's the same sort of idea. And it turns out it doesn't work at all. Like we cannot actually use standard ideas about what probability distributions are because the dimension is too high. I also spoke with some time series specialists, including one colleague in my department at Rice who was up until last year the president of the American Statistical Association, and she's a time series specialist. So I thought I was in good company there when I asked her what the story was. And she's like, yeah, you know what? Your time series might be too long. So, okay. Like, have you tried to use different models? Like, do you know where your change points are? Can you estimate your change points? And so I go, oh man. So there might be some change points which we can maybe estimate. But in any case, we think that the standard time series literature does not actually point us into the right notion of density for what it means to look at an epsilon ball around a specific path. When we work with standard probability theory and we're trying to find, I think most of you have heard of the notion of probability density for a random variable, maybe perhaps, right? Where you take a point in space, and in this case, our points are trajectories like this trace. You take a point in space, you form a ball of radius epsilon around it, you compute the probability of that, then you divide by the mass in whatever Lebesgue measure that you're using in your particular space, and the ratio of those two things as epsilon goes to 0 should converge to a number, and that number would be your density. That makes sense, folks? Like, it's just, that's how we do densities. It doesn't work if your dimension is too high. It just doesn't work. Yeah. And with Julien, we spent months trying to figure this out, right? Yeah, and it wasn't working right. Well, we think we figured it out, but it still doesn't work. So there's more work to be done. But we think we figured out that, of course, we're barking up the wrong tree. The notion of density for infinite dimensional objects, it turns out that there is no such thing as the Lebesgue measure in infinite dimensions. The closest thing that you're going to get is your Brownian motion. Your Brownian motion, the distribution of your Brownian motion is perhaps the closest thing that you might get for a Lebesgue measure in infinite dimensions. But because the Brownian motion itself does not have a stationary distribution, it's hopeless. Yeah. So these objects don't work. So you have to try to modify your notion of density. And there's a natural concept which was developed maybe like 40, 50 years ago, which is that instead of looking at a ball of radius epsilon in Euclidean space around your path, you have to work in the natural space of the path itself. So there, I can't get too technical and we're almost out of time, but it turns out that there's this notion called reproducing kernel Hilbert space. And let me maybe try to write one thing down here if I can. Let me see if I can pull it up on my phone just to show you real quick here in 2 minutes. Bear with me 1 sec. Let me see if I can. So let's say that you're going to have, you're interested in maybe the probability that your ensemble is distant from your trace in, let's say, sup norm. The probability that your ensemble never deviates from this particular trace. What's the probability that it never deviates more than a level epsilon? We can call this S0 of epsilon, and then we can look at, so this is your ensemble, and this is your trace, and then you want to do it for 2 different ensembles, and then you can also look at, sorry, this would be Sx of epsilon, and then you look at the same thing without with x equals 0, and this will be S0 of epsilon. Well, it turns out that there's this general theorem or principle which says that, at least for Gaussian processes, if you divide Sx of epsilon, which is your epsilon, so this is the chance of falling in an epsilon tube around x, and this is around 0, around the constant path, if you will. If you take this ratio and you let epsilon tend to 0, this converges, and it's equal to e to the power negative the norm of x in some appropriate Hilbert space here. It's a Hilbert space with the square and divide by 2. And so as you can see on the right hand side, and so this is if x is Gaussian. And so, okay, on the left-hand side, we're taking the probability of falling in a tube around this trajectory, divided by the probability. This is what we consider our elementary volume element is in infinite dimensions. It's the probability of being near the 0 trajectory, all the time at a level less than epsilon. The chance of that's the volume element I'm sorry, this should be an epsilon, at level epsilon. And this is the same volume element around this different path. So this is the right notion of density. And in fact, I was actually organizing a conference like 2 weeks ago in Texas, and I ran into somebody who's actually a specialist of this. And I just went up to him and I said, can you confirm that my understanding is correct? Because I wasn't really sure even up to that point. He says, yeah, that's right. Everybody knows that there's no Lebesgue measure in infinite dimensions. We have to replace it by some other notion of density. Yeah, for Gaussian processes, this is it, my friend. Yeah, so I'm confident now. Julien, I'm confident. Yeah. Yeah, so this is the right
I
notion
can
of
sleep
density.
at night.
Pardon me?
I can sleep at night finally.
Yeah, that's right. And even with this notion, which Julien and I had investigated, maybe 6 months ago, we really knew that this is what we wanted to look at, because the limit does exist for Gaussian processes. Even that wasn't working for us, which means what? And just 30 more seconds. It means that the limit doesn't exist for us. We get nonsense. It's unstable, whatever. It means that we can't really let epsilon tend to 0 in our particular application. So we're not really sure why that's going on. It might have to do with the fact that our models are just not precise enough that we're using or whatever. So maybe we have to go back to what my colleague was saying, and we need to find the change points and figure out, something a little bit more sophisticated to come up with some better models for our time series. Maybe that'll help us with the fact that our limit doesn't seem to exist. But what we decided to do with Julien, the paper that we just released, is we're not going to let epsilon tend to 0. We're going to fix epsilon and then work from there in order to devise some proper comparisons between ensembles and trace. So that's what we ended up doing empirically. But there's also mathematics to be done behind this. What happens to this theorem if you don't let epsilon tend to 0 and you fix your epsilon? And how true is it that this expression here, as you can see on the right-hand side, this expression here only depends on the distribution of the original process. This Hilbert space depends on the distribution of the original process. The limit exists. What happens if epsilon is fixed, and can we estimate how fast this thing goes to 0? Surprisingly, maybe this is stuff that we should have studied when we were in grad school, my friend. Yeah, we should blame this guy maybe for not teaching it. This is not a well-studied problem. So there's work to be done. But thank you very, very much for your attention today. I appreciate it.
So are there questions or comments?
There were a lot more questions and comments in the previous talk.
Well, so what is your feeling about climate change? Is it happening or is it not happening?
That's how I feel. Oh, is climate change real? Yes.
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 Well, and when you say it's real, what are you meaning as real?
So Julien will correct me, I'm sure. But what I mean is that there's some very strong deterministic reasons why the climate is changing. There's anthropogenic greenhouse gas emissions, which have been going on since the 1850s, right? It's been a long time now. They've really ramped up since 1900. There's also some issue with the data before 1900 was not that great, so we don't usually use it much. But I mean, things have ramped up since the year 1900 that was like 50 or 70 years into the Industrial Revolution. And so, there's a price to pay for that. There's a deterministic reason why the mean average temperatures of the globe have been rising. The deterministic reason is because there's greenhouse gases in the atmosphere, which didn't used to be there. And, we can measure exactly how much, is in the atmosphere now. These measurements are actually extremely precise as how much CO2 there is in the atmosphere, going back, thousands of years or longer. And certainly as the past 150 years, it's no problem at all to measure these things. And we also know where those things came from. So the fact that climate change is real is not a stochastic problem. Climate change is real. It's because humans have put out greenhouse gases into the atmosphere, and not just CO2, there's other ones. Like methane, for instance. I mean, we didn't have a chance to talk too much about, deeper into the applications, but in the case of methane, the biggest thing that we can do in our society today, especially in the US, is to reform the way that agriculture is operated. That's where most of the methane comes from. Methane is 27 times more powerful than CO2 as a greenhouse gas. 40?
It's those cows.
And it depends. Did you know that it depends on what the cows eat and how they eat? Yes, it does. Yeah. So these are things which aren't very hard to change, but it's not a sexy topic, I suppose, when you see a cow and she's burping and that's where the methane comes from. That's not real sexy, right? Yeah.
Depends how you feel about cows.
Yeah, right. Right. Yes, I love cows. Yes, sir.
So
How much of what I said about your field of study was wrong?
well, the part that I want to focus on is you mentioned something about causal analysis.
Okay.
And it's true that in the applied field, partially because that's what undergraduates learn, or even graduate students, most people learn about correlations and most people test for them incorrectly, as you pointed out. And there's various reasons for that. I mean, mostly because most of the theory available assumes that everything is Gaussian and independent and identically distributed, and in practice, it's almost never the case, at least I feel. But in my field, what's more popular now is to say, well, we all learn in grade school that correlation is not causation, but as scientists, we care about causes. So are there, similar ideas that you could apply to causal analysis? Granger causality is no longer very much in vogue, or perhaps some fields of, econometrics, maybe it applies, but there's new approaches to this question now based on causal discovery, particularly in high dimensions and things like that. So
Unfortunately, I mean, I'm not a real specialist on this. I mean, there are folks in my own department who have some deep thoughts about it. It seems like a lot of I've been to a lot of folks who talk about, like modern causal inference in statistics. A lot of people coming through my department give these talks. I listen carefully, try to understand, ask my colleagues. Most of the applications, or in fact, all of them that I've heard, are not to these major wicked problems. They're more about, let's try to figure out, this form of cancer or the genealogical tree over here. It's very, very biomedically oriented. So I feel like the tools that we need, speaking from a position of complete ignorance about the actual substance, but I think that the tools that we need are not being developed now. Which is a shame, yeah.
Other questions or comments? Then let's thank Frederi for a great talk.
So change. So this is all that.
That would be like, I'm going to bring something up where I'm